All right, our next step is to talk about the one-way analysis of variance or the completely randomized design. And in order to do it, let's think about where we have been. Let's think about what we've done so far. We've worked with a single population mean, and the null hypothesis was that the population mean is equal to some hypothesized value, and we were always specifying what that number was. In fact, when we went to the computer, we had to go and put in the value of mu naught in addition to the direction that we were testing. So that was working with a single mean. We then took a look at comparing two means, and we said that the difference between them was equal to, typically we thought of this number here as d naught, the hypothesized difference, but usually it's the value 0. And another way of writing this hypothesis is that mu1 is equal to mu2. And of course the alternative was, no, they're not. One's bigger, one's smaller, they're different from one another. We would say something along those lines. And so now the next step is when we compare three or more means, the natural extension of that would be to say, well, the null is going to say all the means are the same. And so that's what we're going to do in this completely randomized design. That's the way we're going to set the test up. We now use what's called an ANOVA F test. The F refers to the probability distribution that's being used in the computations. Now we could get into that. We could get into t distributions and z distributions and chi-square distributions and f distributions. Or, and some of you guys, your stomach's turning right now a little bit, I can feel it. Or we can rely on our knowledge of p-values and say, you know what, when p is low, we can reject the null hypothesis. We can get rid of it. And so it doesn't matter what distribution it's based on, but that's the distribution that's being used here. It's called the ANOVA F test. So on printouts, you're going to see a column called F, and right next to it will be a p-value. We'll look at that in a bit. The null is going to say the means are all equal, and then the alternative is going to say, excuse me, at least two means differ from one another. Okay, interesting alternative. It doesn't say all the means are different. It doesn't say the first two are different. It doesn't say the first and the third are different. It just says at least two means differ, maybe more, but they're not all the same. That's another way we could say it. Not all the means are the same. It's not a very specific alternative. Okay, the test statistic, the p-value, we're going to get those from the printout. Again, I'll show you where, and in another video, I'll show you how to generate those printouts. But we get those numbers right from the printout, and then you're going to need to make a conclusion. If p is low, we reject the null. We claim at least two of the treatment means differ, and we need to find which ones. At the end of the last video, this was an idea I was going to talk about, and I said, nah, I'm going to hold it. I'm going to wait till the next video. And here's the idea. I thought this would be a better slide to actually make this statement. When we did a test hypothesis on a single mean, when we were up here, when we made the conclusion reject H naught, remember our alternative was either greater than, or less than, or not equal to, but we were able to say at alpha equal 0.05 we reject. There's sufficient evidence to indicate that mu is greater than the value 25 or whatever that number was. We are making it or doing a test hypothesis, and we're getting our conclusion. When we compared two means, when we said the null is that the means are equal to one another, we made a conclusion. At alpha equal 0.05, we reject. There's sufficient evidence to indicate the first mean is bigger than the second mean, or whatever the alternative was. But again, we conducted a test hypothesis, we made a conclusion, and we were done. Now look at what's going to happen. If we reject the null hypothesis and we claim at least two means differ, are we done? Okay, think about it this way. Here I am. I'm out in the garden. I'm growing tomato plants. Someone comes along and says, oh, Mark, we've been testing these different fertilizers. And guess what? There is sufficient evidence to indicate that the mean yield of the tomatoes differs for the 4 different fertilizer types we tested. I'd be like, really? That's good news. So you're telling me that the fertilizer matters? And oh, yeah, the fertilizer matters. Different fertilizers produce different amounts of tomatoes. Now, if I'm a farmer and they're telling me this and I'm like, wow, fertilizers matter, I'm not satisfied right now. I'm not saying, hey, thanks for that information. That's good to know. What's the natural follow-up question? If someone tells you there's a difference, the follow-up question, of course, is where? Which fertilizer type is better? Really, you need to tell me which one's better. And so there's follow-up work to do. Now, if alpha is less than the p-value, if p is high, so if alpha is less than or equal to the p-value, we fail to reject. There's insufficient evidence to indicate at least two means differ. We can't say that any of the means differ. We haven't detected any differences. We would stop them. We would be done. And I know from your seat right now, you're probably thinking, yeah, I like that. Look at that. Look at this word right here. We love this word. We're students. We want to stop. We want to be done with this. But in reality, that's not the conclusion you really want, because ultimately you want to gain knowledge. And by failing to reject, you're not gaining any knowledge. You're saying, yeah, I really can't say there's a difference in the fertilizers. That's not what we want to hear. We want to hear that there is a difference. And we want to be able to grow more tomatoes in the example I'm using. Obviously, I use the subscripts here from the example I ended the last video, working with, what was that, the Stat 2 grades of different majors. So I'm mixing up my examples a little bit, but hopefully that idea makes sense. It's the first time, it's not the last time, by the way, we're going to see this probably the rest of the semester, but it's the first time we conduct a test hypothesis, and it leads us to do more work. So we're going to take a look at an example. But before I do that, let's talk about assumptions. And these assumptions are going to follow some things we've talked about earlier in the semester, words like random and independent and normality and equal variances. Well, look what I have here. All of them come out to play. Okay, we need random and independent samples. Every treatment has to be independently selected from. We need to randomly and independently select. So if I was going to be talking about students and the majors and trying to figure out grades, I would want to randomly select students from each of the 4 majors and compare their grades. The distribution of the response variable needs to be approximately normal. In other words, the grades that I see for each of the majors need to be approximately normal. The variation in the grades for each of the majors needs to be the same. Those 4 assumptions need to be true for any analysis of variance. Sometimes when we were comparing 2 means, the assumptions we made depended upon the scenario. If we had large samples, we had some assumptions. If we had small samples, we had others. Sometimes we had equal variance assumptions, sometimes we did, and it was a little bit more confusing, a little bit more thought needed to go into the assumptions when you were comparing 2 means. When we switch to this F distribution, and when we compare 3 or more means, we need these assumptions all the time. Now, when you're going to be writing assumptions for like project, I want these in the words of the problem. You're talking about a response variable. Well, whatever you're working with, there will be a response variable. Don't state it that way. Tell me the prices or the sizes or the mileages or whatever it happens to be for your models of vehicle, for your locations of homes or apartments, whatever it happens to be. But state this, and this is a statement throughout the semester, state your conclusions, your assumptions, your interpretations, whatever you're working with, state them in the words of the problem as much as you can. All right, so those are the assumptions that are necessary for the completely randomized design. All right, so let's take a look at an example. There's a data set called the Diamond data set that I'll make available to you. And it contains a bunch of information on, of course, diamonds. And some of the variables that it contains, the size of the diamond, the number of carats, the price in dollars, and on the qualitative variables there's color, clarity, and then the certification group. And you can see there in parentheses, the certification group is the group that looks at the diamond and certifies its quality, its color, its clarity, it's all this, and it's the one that's providing the data, really. But there are 3 different certification groups, GIA, HRD, and IGI. There are 5 colors. They're rated as D, E, F, G, H, and I. There are 5 clarities. These are really fun ones. IF, VS1, VS2, VVS1, and VVS2. And so we have a whole bunch of variables. And so in the example here, the data set I'll give you, you can play around with it and try some other things, but we're going to select one quantitative variable and one of the qualitative variables, and we're going to do a one-way analysis of variance. Okay, so the example that I want to work with, we're going to try to look at the size. Is the number of carats or the size of the diamond, does it depend on that? So size is going to be our response variable. The factor that I'm going to consider is the clarity. And the factor levels, well, you see the 5 levels there, I just mentioned them. And so really what I'm asking is the average size of the IF diamonds the same as the average size as the VS1 or the VS2 or the VVS1 or the VVS2? That's what we're going to be working with. Okay, so we have a response variable as size, and what I'll encourage you to do with this data set is to go and play around. Change it to price. Those are your 2 possibilities. You can either do size or price. For the factors, you can do clarity, you could do color, you could do certification group. Obviously, as you change the factor levels are going to change. But I want you to do one-way analysis of variance, and so the factor levels are going to be the treatments. We have 5 treatments that we're going to work with in this particular example. And so the test that we're going to set up, our goal is to compare the means that I mentioned earlier. That's how we're going to set up the test. We're going to set it up to say that those means are all equal. The mean size of those 5 clarity levels are all the same. And the alternative says, no, they're not. The alternative says at least 2 means differ. And so I've mentioned to you before, and I'm going to continue to mention to you, that when we're doing test the hypothesis, figuring out what the test is, what the null and the alternative test, the HO and the HA for the test is, that's always on you. That's reading the problem and being able to understand this is what we're trying to test. What you will find as you get more and more experience, as you identify the null and the alternative, that's going to take you to different menus within the software package that you're working with. I'm going to go to the one-way analysis of variance. Why one-way AOV? Because I have 3 or more means that I want to compare. I have 5 means that I want to compare. So it leads me to the one-way analysis of variance. And when I get to those menus, it asks me for the response variable, the factor. It calls them different things typically. Usually it's like dependent variable, categorical variable. There's a lot of different names that you might find. But it asks me, what are you trying to do? And when I put in that information, I'm going to get something that looks like the following. There we go. That's the printout that I get. And depending what software you use, I use something called statistics, which is what I'm having you guys work with on your project. But whatever software you use is going to give you a different look, but it's going to have the same information. Ultimately, it's going to have these 2 pieces over here. And we really like this guy. Look at how low that p-value is. But identifying the null and the alternative, that's something you're going to have to do that gets you to a printout. The type of null and alternative sends you to a menu that generates the printout that you want, and now it's your job to get in there and do the interpretation. How do you interpret a low p-value like that? Well, and I used alpha 0.10 here. I could have used any number really, right? Because p is so low. We're going to reject. We're going to say at least 2 means differ. I'm going to come up here and take a look. When I reject the null, I'm saying that at least 2 means differ, but look at the way I'm saying it. There is sufficient evidence to indicate that the mean caret weight, that's the response variable, right? The mean caret weight for the 5 clarity levels differs. I'm not saying they're all different. I'm saying at least 2 of them. There's differences out there. Of course, I'm going to ask you, what are you going to do next? We need to find them, right? At alpha equal 0.10, we reject. There's sufficient evidence to indicate the mean caret weight for the 5 clarity levels differs. Now, what assumptions are necessary? Random and independent samples. The response variable, the caret weights, the sizes for the 5 clarity levels are all approximately normal. And the variation in the caret weights, the variation in the sizes for the 5 clarity levels are all the same. Those are the assumptions. Now, I'm going to have you state the assumptions now. Later in the class, I'm going to have you check those assumptions. Again, we're going to do it under the umbrella of regression analysis. So some of the things we're doing now, this analysis of variance, we're sticking with one-way analysis of variance because I know the 2-way and the more complicated designs will get some of those ideas with our multiple regression. Same thing with the assumptions. Right now, I want you to state the assumptions. Later on in the semester, we're going to go ahead and take a look at checking those assumptions and see how we do that. It's pretty straightforward. So I would expect you with this one-way analysis of variance, at least through this video, I would expect you to be able to identify the null and the alternative, obviously identify response variables and factor levels and treatments, be able to state the null and the alternative, be able to find on a printout the test statistic, that's the value in the F column, and the p-value, and then, as always, be able to interpret a p-value. Also, I'd expect you to be able to state the assumptions that are necessary for analysis to work, which leads us to our next step. Rejecting H0 indicates at least 2 treatment means differ. I've just said at least 2 caret weights differ for the 5 clarity levels, but the obvious question is which ones? And so the next step is to investigate that a little bit. Which means differ? And good news for us, I guess bad news for us first, is that there's more work, right? We just completed a test hypothesis. We made our conclusion, and we're not done. We got more work to do. So that's bad news. The good news is that the work that we're going to do looks similar to something we've done before. We've obviously just done a test hypothesis. Now we're going to follow it up with some Confidence intervals. And so we're relying on these two tools, the confidence intervals and the test hypothesis. So come on back and watch the next video, and we'll talk about how we find out which means we're in fact the ones that are different. So long.